3IATLAS just did something NASA can't explain, and the timing is disturbing. A cosmic documentary sleep story. Part 1, opening the question. Before we dive any deeper into this mystery, I just want to say something real quick. Making these documentaries, it's a ton of work. Days spent digging into research, writing scripts, editing, trying to share stories that are both accurate and actually interesting. If you like what I do, if these stories about the unknown get your brain buzzing, I'd really appreciate it if you subscribed or left a like. It's not just about numbers. It tells me this stuff matters, that we're all curious together. Thanks for being here. Something moved. Not the slow drift of an asteroid we already knew, not the soft swing of a comet keeping its ancient appointment. This was different. It came from somewhere out in the dark, from between the stars, and slipped through the inner solar system while every telescope on Earth, and a few above it, tried to keep up. Then it did something no one expected. At first, the data barely registered. A few odd blips, easy to blame on noisy instruments or some calibration issue. But then more observatories started seeing it. Same weirdness popping up everywhere. NASA's tracking flagged it too, all on its own. That's when people started talking, not in press releases or headlines. Quietly, late at night, in emails and last-minute calls. Scientists choosing each word carefully, trying to describe something they hadn't really seen before. They call it 3IATLAS. The name tells you a lot and honestly not much at all. 3I means it's the third interstellar object we've ever confirmed. Atlas is the name of the sky survey that spotted it, a system of robotic telescopes in Hawaii and Chile, always scanning for anything that moves or changes, anything that doesn't fit. July 2025, that's when they found it. At first, it seemed like just another interstellar comet. We figured it'd do what the others did. Show up, swing by the sun, shed some dust, fade back into the dark. All by the book. The math lined up. Nothing too exciting. But 3IATLAS didn't stick to the script. That's why we're here tonight. Because when something from another star system starts acting in ways our models can't predict and the timing looks less like chance and more like a pattern, you start asking tough questions. The kind you can't answer right away. The kind you might not want to answer at all. Let's get this out of the way. This isn't a story about aliens. Really. It's about what happens when the universe throws you something that doesn't fit in your neat little boxes. When the data refuses to play along, when you have to admit there's more going on out there than we thought. So, here what we're going to do. We'll walk through the timeline. We'll look at what NASA saw, what independent teams noticed, and the stuff that still doesn't add up. We'll see the moment people stopped feeling sure, when routine checks turned into frantic follow-ups, and when the official language quietly shifted from cometary activity to needs more investigation. And we'll have to sit with not knowing. That's never comfortable, but honestly, that's where the real discoveries start. In that strange gap between what we expect and what actually happens, when reality refuses to match the math. Quick thing before we dive in. This channel is all about cosmic documentary sleep stories, slow, thoughtful explorations of what's happening in our solar system and beyond right now. No clickbait, no shortcuts. If you care about the real work of figuring out what's out there, really out there, subscribe. Give this a like if you want more deep dives like this, because there's always more. The universe isn't running out of surprises anytime soon. All right. Let's start where all good mysteries do, with the moment everything seemed perfectly normal. Part 2, the expected discovery. Finding things in space follows a kind of beat. There's a routine, almost like clockwork. Telescopes sweep across certain patches of sky. Software checks photos from different nights, hunting for anything that moves. If something pops up that wasn't there before, algorithms flag it. Then real people, astronomers, step in. They look at the flags, figure out rough orbits, guess how bright the thing is, label it. Usually it's just another asteroid. Sometimes it's a comet. And once in a while, it's something stranger, something from outside our solar system. Atlas knows this rhythm inside out. 2 telescope stations, one high up on Halakala in Hawaii, the other down in Sutherland, South Africa, work together, along with scopes in Chile. Between them, 4 wide-field telescopes cover the whole visible sky every couple of nights. The original goal here was planetary defense, spot asteroids that could hit Earth. But while watching for those, Atlas catches everything else: comets, distant supernovae, variable stars, even the rare interstellar visitor. Up on Haleakala, more than 10,000 feet above sea level, the observatory sits above most of the atmosphere's moisture. That makes a huge difference. When the trade winds sweep the clouds down below, the sky turns pitch black, about as dark as it gets in the northern hemisphere. At sunset, the domes roll open on their own and the robotic telescopes kick into gear. No one has to be there to start things up. The system just scans, night after night, quietly building up a record of everything that changes out there. On July 1, 2025, something new popped up: 3IATLAS. The software flagged it right away. Faint dot moving against the background stars. The orbit numbers showed it wasn't bound to the sun. Too fast, a hyperbolic path. That's the classic sign. This thing came from interstellar space. Not captured, just passing through. People got excited, of course, but honestly, it wasn't such a shock. We'd seen this twice before. 1I/Oumuamua in 2017, then 2I/Borisov in 2019. Now, here was number 3. NASA's Jet Propulsion Lab in Pasadena quickly started tracking 3IATLAS. The Minor Planets Center in Cambridge gave it an official designation. Observatories everywhere across the US, around the globe, turned their telescopes toward it. Hubble got some time. James Webb added it to the list. Ground-based teams in Arizona, Hawaii, Chile all coordinated efforts. That's how modern astronomy works. Everyone collaborates, shares data, and tries to catch as much as possible in real time. At Lowell Observatory in Flagstaff, Arizona, astronomers set up observing runs on the big 4.3-meter Discovery Channel telescope. The place sits at 7,200 feet in the Coconino National Forest, some of the clearest skis you'll find in the lower 48. The crew there specializes in small stuff: asteroids, comets, Kuiper belt objects. Adding 3IATLAS, obvious move. This is what they do. The first observations told a familiar story. Small nucleus, maybe a few hundred meters across, maybe up to 5 kilometers. Hard to nail down because it's wrapped in a coma, a cloud of gas and dust, cooked up as ice turns straight into vapor. Spectra showed the usual mix: water vapor, carbon dioxide, carbon monoxide, dust. There were a few quirks, like a lot of carbon dioxide compared to water, but nothing totally out of left field. Interstellar comets form around other stars, different chemistry, different mix. That's normal. The orbit was interesting, but nothing wild. 3IATLAS dove into the inner solar system on a steep path, swung close to the sun at the end of October 2025, about 1.4 astronomical units out, just inside Mars's orbit. After that, it headed back out, making its closest pass by Earth in mid-December at about 1.8 AU. Close enough to study, not close enough to worry about. The math all lined up. Gravity from the sun, a nudge from Jupiter, but nothing unpredictable. At first, everything went just the way you'd expect. New comet shows up, the data starts rolling in. Scientists tweak their models, crank out papers, get ready for talks at conferences. Grad students dive into the numbers for their dissertations. It's science doing what science does best. Something new pops up, the whole community jumps in, gathers what they can, and slowly the picture gets clearer. You could feel the confidence. Not the loud, chest-thumping kind, but the calm, steady assurance that comes from dealing with something familiar. Comets, we know them. Spacecraft have flown past, landed, even grabbed pieces to bring home. We understand the basics. Sunlight warms them up, the ice turns to gas, jets shoot out and nudge their orbits. Sure, the jets go off in all directions because comets are lumpy and spin around, but the big picture makes sense. Comet science is an old, well-traveled road. Over at NASA Goddard, teams ran computer simulations of 3IATLAS, throwing in different mixes of water-ice, carbon dioxide, carbon monoxide. They played with nucleus size, spin rate, how shiny the surface was. Each run spit out predictions: how bright the comet should get, how much gas it would throw off, how the coma would swell as it got closer to the sun. No simulation is perfect, none ever are, but they gave everyone a solid starting point. a way to make sense of the mountain of data coming in. So 3IATLAS was supposed to be just another entry in the catalog. Sure, it's cool because it came from another star, and it's a rare chance to peek at stuff from a whole different system. But at its heart, it looked like all the other comets, a frozen leftover from some far-off solar system, drifting for eons, catching a little sunlight before vanishing again. Teams at NASA Ames, Goddard, and a bunch of university observatories settled into the routine. Long nights at the telescope, hours staring at noisy images, spreadsheets crammed with numbers. This is the real work of astronomy, not flashy breakthroughs, just slow, steady collecting and double-checking, building up enough evidence to trust what you're seeing. At the University of Hawaii, folks pulled together observations from all over the islands. The twin Keck telescopes on Mauna Kea, each a 10-meter giant, grabbed spectra to pick apart the comet's chemistry. The IRTF, also on Mauna Kea, looked for heat signals, measuring temperatures and how heat spread through the nucleus in Coma. The Pan-STARRS survey telescope at Haleakala tracked how the brightness changed night after night, and for a while everything fit. 3IATLAS acted like a textbook comet. It kicked off gas and dust as it neared the sun, got brighter, its coma spread out. Nothing weird, nothing unexpected. Amateurs jumped in too. All over the country, backyard astronomers with scopes big and small started tracking this thing. They measured its position, helping pin down the orbit. Snapped photos to watch how it changed. Sent their data to groups like the American Association of Variable Star Observers, adding to the pool of knowledge. From Texas suburbs to New England backyards, the Pacific Northwest to the New Mexico desert, these hobbyists spent night after night under the stars, guiding their telescopes as 3IATLAS crept across the sky. They caught photons that had traveled trillions of kilometers from a comet born around a star we'll probably never even find. There's something kind of amazing about that, regular people, driven by curiosity, helping to unravel the secrets of the universe. Science, wide open. Discovery for everyone. But then came perihelion. The word literally means closest to the sun. For comets, perihelion is when everything happens. Maximum heating, maximum sublimation, maximum activity. It's also the most difficult time to observe from Earth because the comet is often too close to the sun in the sky, lost in solar glare. Ground-based telescopes can't point that close to the sun without risking damage to sensitive electronics and optics. Even space-based instruments have pointing restrictions to protect their instruments from direct solar radiation. 3IATLAS swung around the sun on October 30, 2025. For about a week before and after, you really couldn't see it from Earth. The sun just got in the way, completely blocked our view, but not everyone was in the dark. Some spacecraft stationed elsewhere in the solar system managed to keep an eye on it. Stereoway, one of NASA's probes out ahead of Earth in its orbit, had a good angle and picked up part of the action. SOHO, hanging out at the L1 point between us and the sun, caught a few glimpses using its coronagraphs. Still, the detailed stuff, the kind of sharp imaging, precise tracking, and fancy spectroscopy you get from ground telescopes or Hubble, was out of reach. Pretty much impossible. Honestly, this happens all the time. Anything that swings close to the sun will go through this solar conjunction blackout. Astronomers are used to it. They cram in as much observing as possible before the sun blocks the view, then pick things up again when the object comes back out. There's always a gap in the data, always a stretch where you're working blind, leaning on predictions and hope instead of direct evidence. It's annoying, sure, but it's just the reality of watching the universe from Earth, not so flexible orbit. But this time, when 3IATLAS popped back into view, the data didn't match up. Something was off. Not in that dramatic, Hollywood way where a comet splits into pieces or suddenly bursts into wild brightness. No epic fireworks, no nucleus shattering. It was subtler than that. It took days for anyone to even notice and weeks before people were confident. And even now, nobody's got a solid answer. The orbit had changed. Not by a lot, not enough for CNN or BBC to start sounding alarms, but enough for NASA's tracking software to throw up red flags. Enough that independent teams running their own calculations weren't coming up with the same numbers as before. You could run the math every way you liked, but you kept landing at the same unsettling spot. Something nudged 3IATLAS right when we couldn't watch, right in the blind spot, right in the data gap. So that's where this story really gets interesting. Part 3. When the data refuse to behave, there's a reason. Orbital mechanics is called a hard science. Newton wrote down the basics in the 1600s. Kepler's laws nailed the patterns. Over the centuries, we've polished the math, thrown in relativity for the tough cases, accounted for every gravitational tug, and built computer models that can predict exactly where a planet or spacecraft should be years in advance. We can send a probe millions of kilometers and have it show up on time, down to the minute. Space is orderly, predictable. You think we had it all figured out. Except, well, not always. Comets mess with the system. They don't just coast along on gravity, they're active. As they get close to the sun, gas jets shoot out, giving them little pushes here and there. These non-gravitational forces are real, and everyone who's studied comets knows about them. The catch: they're tough to predict. You need to know things you usually can't measure from far away. How fast is the comet spinning? Where are the active spots on its surface? How much gas is blasting off, and which way? What's the actual mass of the core? All these details pile on uncertainty and make it that much harder to say exactly where the comet will end up. But there's uncertainty, and then there's what happened with 3IATLAS. The first sign that something was off came from JPL's tracking system. The Jet Propulsion Laboratory maintains the authoritative database for solar system objects. The Horizon System, a repository that contains orbital elements for hundreds of thousands of asteroids, comets, planets, moons, and spacecraft. Their software constantly ingests new observations from telescopes around the world, recalculates orbits using sophisticated algorithms, issues updates. It's an automated system for the most part, designed to handle the fire hose of data coming from modern sky surveys. In early November, shortly after 3IATLAS emerged from solar conjunction, the automated system flagged an anomaly. The object's observed position didn't match the predicted trajectory within expected error margins. The residuals, the differences between observed and predicted positions, were larger than they should have been. This happens sometimes. Initial orbital solutions for newly discovered objects are always approximate. As more data comes in, the orbit gets refined. Usually, the refinements are minor. The object is a bit faster or slower than first calculated, or the trajectory is slightly more or less inclined to the ecliptic plane. Normal stuff. The algorithms account for this. They're designed to handle noisy data, sparse observations, uncertainties in timing. When the folks at JPL started digging into the weirdness with 3IATLAS, they spotted something that didn't sit right. This wasn't just a random blip. There was a pattern. The object sped up, and not in the wild, tumble-any-which-way style you'd expect from a comet spinning out jets here and there. The acceleration pointed in a certain direction. It felt deliberate. Dr. David Farnakia, who knows small bodies backward and forward, he's charted orbits for hazardous asteroids, helped steer spacecraft to comets, you name it, took a closer look. He's seen every flavor of cometary acceleration, knows what outgassing does to a trajectory. But the numbers he got from 3IATLAS made him stop and think. Naturally, people doubted. Maybe those early observations before perihelion weren't as solid as everyone hoped. Maybe one observatory's data had some sneaky systematic error. Or maybe the atmosphere messed with the images and nobody caught it the first time. Astrometry, measuring the object's position against the stars, can slip up in tiny ways. In astronomy, false alarms are just part of the deal. Stuff looks weird, then vanishes after a fresh round of data checks. So teams got to work. Independently too. NASA's Goddard crew in Maryland ran their own orbit models using different software, new math, even tweaked gravitational assumptions. Over in Hawaii, the Atlas team went back through every image, recalibrated, double-checked every measurement. ESA's Near-Earth Object Coordination Center in Italy did their own runs with European data. Folks at Lowell Observatory and the Minor Planets Center threw their hats in as well. They all landed on the same answer. The acceleration was real. Sure, it was tiny, just a few meters per second change in speed, nothing wild for something in space. That's maybe as fast as someone jogging, but it showed up in the data clear as day again and again. And it stuck around. This wasn't a one-off spike. The change in velocity stretched over hours, maybe longer, right as the comet swung by the sun. Now comets do this kind of thing all the time. Outgassing can push them off course. It's practically textbook. Take Comet Encke. Astronomers have watched it for 2 centuries, and its path drifts because jets of gas shoot out, acting like a bunch of mini rockets. The direction of that push comes down to which patches of ice are venting and how the whole thing spins. So nobody was asking if outgassing could do the job. The real question was, did the acceleration fit with what you'd expect, given how big 3IATLAS is and how much activity it showed? To figure that out, you need to know how much gas it's throwing off. You estimate from how bright the coma looks, check the spectra for different gases, model how ices vaporize at different distances from the sun. You tally up water, carbon dioxide, carbon monoxide. You see how much dust gets blasted off. Basically, you do the math on how much oomph all that escaping stuff should give the nucleus. And here, where things broke down. When everyone crunched the numbers, the acceleration was just too big for the amount of outgassing they actually saw. If jets were pushing that hard, the comet ought to be much brighter, way more active, just spewing out more gas and dust than anyone observed after it zipped past the sun. Unless the outgassing happened during perihelion, during the observation gap, and then declined afterward. That's possible. Comets do have outbursts, periods of enhanced activity that can be brief and unpredictable. Solar heating might have triggered a sudden release of volatile material that was buried beneath the surface, insulated from previous solar exposure. The outburst could have been intense enough to alter the trajectory, but short-lived enough that it was mostly over by the time ground-based observations resumed. This became the working hypothesis, not because it was the most satisfying explanation, but because it was the least problematic. It kept 3IATLAS in the category of unusual but natural. It didn't require any exotic physics or uncomfortable implications. Comets are temperamental. They do weird things sometimes. The nucleus might have had subsurface pockets of highly volatile ice that vented explosively when exposed to intense solar heating. Case closed. Except the data kept not quite fitting. A team at the University of Maryland kept a close eye on the comet using spectroscopic data from Apache Point Observatory in New Mexico. They tracked water through ultraviolet hydroxyl lines and carbon dioxide in the infrared. The gas output bounced around a bit from day to day, pretty normal since a comet spins and sunlight hits different parts. But overall, things stayed steady before and after perihelion. No big outbursts, no sudden gas spikes. Observers everywhere saw the coma's brightness rise smoothly as the comet neared the sun, then drop off just as smoothly after. Nothing weird. No signs of a wild, violent outgassing. Then came the morphology work. If you're not familiar, morphology just means looking at the shape and structure, in this case, of the comet's coma and tail. Active patches on a comet spit out jets, which show up as streaks or fans in photos. By watching how these features shift over time, you can figure out which parts of the comet are active and how that changes as it spins and moves through space. Throughout November and December, all kinds of observers, pros, amateurs, big telescopes, backyard setups, snapped images of 3IATLAS. The folks at Lowell Observatory, the University of Arizona's Lunar and Planetary Lab, and plenty of amateur astronomers all got deep shots over several nights. What they saw was odd. The coma looked weirdly even and perfectly round, just a smooth, symmetric cloud around the nucleus. No obvious jets, no lopsided features pointing to one-sided outgassing strong enough to explain the comet's acceleration. Sure, maybe jets were there, just hidden. Sometimes you can't see them from Earth, depending on the angle. If the active spots are facing away or the jets shoot out sideways from our point of view, they might blend into the background. Faint jets can get lost in the glow, too. Or maybe the comet's rotation axis was tilted in such a way that jets never form the typical fan patterns. But honestly, it's also possible that outgassing isn't the whole story. Maybe something else boosted the comet's speed. That's the sort of thing that keeps scientists up at night. This is where things get tricky. If the usual comet physics can't explain the acceleration, what can? One idea is that the answer lies inside the comet. Maybe 3IATLAS has big hollow spaces stuffed with volatile ices. Imagine a pressure cooker. Ice trapped in sealed pockets heats up, pressure builds, and then, crack, the chamber bursts open and gas explodes out. That would create a quick, strong push, but not necessarily leave behind big jets long enough for us to catch in photos. Comets are basically loose piles of ice and rock, so internal voids make sense. Actually, spacecraft have seen this before. Remember Comet 67P/Churyumov-Gerasimenko? ESA's Rosetta mission found it was full of porous cavities and chambers. Some of those probably hid volatile gases that vented out when warmed. Another possibility, the nucleus could be cracking apart. As a comet nears the sun, it heats up and cools down over and over. That cycle stresses the surface, expanding by day, shrinking by night, and eventually cracks form. If one of those cracks breaks open to reveal fresh, supervolatile ice, you get a sudden burst of gas. That's the kind of thing that happened to Comet Shoemaker-Levy 9, which broke up before crashing into Jupiter in 1994. In that case, Jupiter's gravity played a big role, but the basic idea holds. Cracks and sudden exposure can trigger dramatic activity. Both of these scenarios are plausible. Both have been proposed in scientific papers about 3IATLAS. Both allow the object to remain firmly in the natural comet category. But both also require specific, somewhat unusual internal conditions that we can't directly verify because we can't see inside the nucleus. We're inferring structure from surface behavior, which is always uncertain. And then there's the timing question. Why did this happen at perihelion during the observation gap? From a purely physical standpoint, perihelion is exactly when you'd expect a comet to be most active. It's closest to the sun, receiving maximum solar heating, so it's the most likely time for outbursts, structural failures, or any other activity driven by temperature changes. The timing makes perfect sense from a thermodynamic perspective. But it's also the least convenient time from an observational standpoint. The one period when precise tracking is most difficult, when spectroscopic monitoring is limited, when high-resolution imaging isn't possible from ground-based facilities. If you are going to have an event that changes a comet's trajectory, perihelion is both the most likely time physically and the most frustrating time scientifically. Some researchers can't help but wonder, off the record of course, if there's more to that coincidence than meets the eye. Probably not. Perihelion is just perihelion. Physics doesn't care whether we're watching or not. When the sun's heat is strongest, that's where the action is. Still, people love patterns. When something weird happens right when we can't see it, that nagging feeling shows up. A little voice suggesting maybe the timing isn't just luck. But honestly, that road leads straight to wild guessing. Science needs things you can actually test. Suspicious timing isn't proof. You just have to shrug, admit it's annoying for the data, and move on. That's what most researchers did, at least when anyone was listening. Then there's the weirdness with the direction of the acceleration. If you sit down and break out the math, split the acceleration into parts along and across the comet's motion, it doesn't look random. The acceleration points in a way that, if it kept up, would nudge 3IATLAS onto a slightly different path through the outer solar system. It's not just a speed change either. The acceleration has both a long track and sideways components, so the comet's direction shifts too. After perihelion, the orbit isn't quite the same as before, even when you factor in the sun and all the planets tugging on it. Does this matter? Maybe, maybe not. Orbits get jostled all the time. Outgassing, gravity from planets, you name it. The fact that this push went a certain way could be pure coincidence. Outgassing jets shoot off in any direction, depending on where the active spots are and how the nucleus spins. There's no rule saying the thrust needs to line up with anything special. But then you start stacking up the weird bits, the size of the acceleration, the missing jets, steady production rates, the timing during the observation blackout, the specific direction of the velocity change. It starts to feel like a pattern you can't just wave away, not proof of anything wild, just a bundle of oddities that don't quite add up. Any one of them you could explain. All together, though, it's hard not to get a little uneasy. And then the polarimetry throws in another twist. Polarimetry measures how light gets polarized bouncing off particles, stuff like size, shape, and makeup of the dust. A group at Mauna Kea's 2.2-meter telescope took a close look at 3IATLAS's Comet in late November and early December. What they saw was strange. The linear polarization changed with phase angle, the angle between the Sun, Comet, and Earth, in a way that's just not typical for comet dust. Usually, comets show negative polarization at small phase angles, positive at big ones, and flip around 20 degrees. That's a well-trodden path, checked and double-checked on dozens of comets for decades. 3IATLAS showed the same general trend, but its polarization numbers came in lower than expected. At a phase angle of 30 degrees, where most comets land somewhere between 15% and 20% linear polarization, 3I/Atlas barely hit 10%. That points to its coma dust being different. Maybe the grains are smaller, or maybe their makeup, structure, or shapes just don't match what we see in typical comets. Smaller dust grains would also explain why the coma looks faint, even though there's plenty of gas coming off. Big grains scatter sunlight really well, so the coma glows. Small grains, not so much. If 3IATLAS is mostly producing tiny submicron grains, less than 1,000th of a millimeter across, the coma stays dim even with all that gas. But small grains don't just make the coma fainter. They also respond differently to sunlight. They shoot away from the nucleus faster than big grains, carried out by the escaping gas, then pushed farther by sunlight itself. You'd expect this to puff up the coma, making it bigger and more spread out. Strangely, though, the coma around 3IATLAS looked pretty tight and compact, hugging the nucleus. So that's another odd detail. Thermal infrared readings from NASA's IRTF up on Mauna Kea gave us surface temperatures. At the comet's distance from the Sun in mid-December, about 1.6 AU, you'd expect 200–220 Kelvin on the surface. That's cold enough to keep water ice mostly frozen, but it's warm enough to let carbon dioxide and carbon monoxide sublimate and drive activity. The numbers matched what you'd get from plain old sunlight warming up a bare surface. No mysterious heat, nothing churning inside. The comet just soaked up sunlight and re-emitted it in the infrared, exactly what you'd expect from a chunk of rock and ice. Honestly, it's a relief. If 3IATLAS was pumping out more heat than solar energy could explain, things would get weird fast. We'd have to start thinking about exotic chemistry or even artificial activity. But the data was boring in the best way, just normal physics. Several teams tried radio observations. The ALMA array in Chile, one of the world's most sensitive setups, pointed its dishes at 3IATLAS in early December, looking for molecular lines. ALMA can pick out specific molecules thanks to their unique fingerprints in the radio spectrum. Water, carbon dioxide, carbon monoxide, methanol, hydrogen cyanide, formaldehyde, all of them have telltale signals. ALMA picked up carbon monoxide and carbon dioxide, backing up what optical and infrared data already hinted. But here's the kicker. The Co-to-Co2 ratio was wild. For every molecule of carbon dioxide, there were about 5 molecules of carbon monoxide. That's the reverse of what we see in solar system comets, where Co2 usually dominates by a huge margin, ratios more like 20:1 or 50:1. This flipped ratio screams that 3IATLAS came from a place very different than our own backyard. Maybe its star was different, Or maybe it formed in a cold part of its disk where carbon monoxide could freeze out while carbon dioxide couldn't. Methanol was barely there, just a faint blip above the noise. It's an organic molecule, one of the raw ingredients for more complex chemistry. Spotting it in an interstellar comet is a neat data point. It hints at what kinds of organics other solar systems might have. But honestly, methanol is usually a bit player in comets anyway, so its low abundance isn't shocking. No other complex organics turned up in the data. That doesn't prove they're missing. ALMA's amazing, but it still has its limits. Low abundance molecules might just be too faint to catch. You need to get closer, watch longer, or actually sample the material to get the full chemical picture. By mid-December 2025, as 3IATLAS made its closest pass by Earth, about 1.8 AU out, the mood in the scientific community was a mix of excitement and confusion. No panic, no wild theories, just a sense that this object was refusing to fit neatly into anyone's models. Papers started to pile up, hedging their bets. Needs more study. Challenges standard models. Hints at complex internal structure. Further observations recommended. NASA's official position remained that 3IATLAS is a comet exhibiting unusual but not unprecedented behavior. No evidence of anything artificial or technological. No anomalous radio signals detected. No spectral signatures that would indicate manufactured materials. All observations consistent with a natural object, albeit one with some peculiarities that are still being studied. And that's where things stand right now. January 2026. The object is fatting as it moves away from the Sun and Earth. Observing opportunities are declining. Within a few months, 3IATLAS will be too faint for all but the largest telescopes. The Keck telescopes on Mauna Kea can still track it. The Very Large Telescope in Chile can still gather spectra. Hubble, if allocated time, could still image the nucleus and coma. But as the comet recedes, the signal-to-noise ratio drops. The data quality degrades. The window to gather high-quality data is closing. What we're left with is a collection of observations that don't quite add up. An acceleration that seems too large for the observed outgassing. A coma that appears too symmetric for the kind of asymmetric jets you'd need to explain the trajectory change. A timing that coincides perfectly with our inability to watch closely. And a new orbit that's different enough to notice, but not different enough to demand exotic explanations. It's the kind of scientific puzzle that keeps researchers up at night, not because it points to anything sensational, but because it highlights the limits of what we can know from a distance, the gaps in our understanding, the assumptions built into our models, the difference between what's plausible and what's proven. And maybe that uncertainty is precisely what makes this story worth telling, because this is what real science looks like. Not neat answers and tidy conclusions, but messy data, competing hypotheses, and the slow, patient work of trying to figure out what actually happened while the object responsible is already disappearing into the cosmic distance. Part 4, The Silence of Science, and the limits of knowing. There's a certain tension that hangs over astronomy. It's not just about missing data or wild guesses. It's more like this ongoing awareness that no matter how good your instruments are, there are always limits. Telescopes can only see so much. Angles are never perfect. Time, always running out. And sometimes the universe just refuses to give you all the answers you want. This feeling isn't just in the science itself. It seeps into the spaces between conference talks and published papers. You feel it in the quiet hours after a night at the telescope, staring at data that doesn't line up with your predictions, wondering if the issue is with your equipment or your understanding. It pops up in those long email threads with colleagues, when everyone's trying to figure out if they're seeing something real or just random noise dressed up as discovery. With 3IATLAS, that sense of tension has become almost physical. No one talks about it in press releases. You won't see it in official statements, but it's there always. It hums beneath every observation, every calculation, every debate about what this object might be doing as it slips out of view. Part of the challenge is just the way astronomy works. You don't get to make bold claims unless you've got the data to stand behind them. Wild speculation has no place in the journals. If you spot something strange, your first move is to rule out every boring explanation you can think of. This kind of caution is part of what keeps science honest. It's a good thing most of the time. But it also means that when something truly weird shows up, the default reaction is to doubt it, to look for mistakes, to assume there's a simple answer waiting just out of sight. At NASA's Ames Research Center, the team watching 3IATLAS has been careful with their words. Inside, they admit the trajectory change is real and doesn't fit neatly into the standard models. But in public, they're cautious. Here's an interstellar comet acting a bit odd. We need more data. The analysis is ongoing. We'll have updates when we know more. That's not dodging the issue. That's science doing what it's supposed to do. Don't jump to conclusions. Gather more evidence. Test every idea. Let the rest of the community take a look before you say anything big. The trouble is, 3IATLAS is fatting fast, and the window for observation is closing. There's a sense that, no matter how hard they try, the data might never be complete enough to answer every question. Some astronomers have started digging through old images, hopping to spot 3IATLAS before it was discovered. Teams at the University of Arizona and Lowell Observatory are combing through sky surveys, looking for any trace of the object before July 2025. If they find anything, it could be huge. It would stretch the timeline back, help pin down the orbit, maybe even reveal when things started to get weird. But so far, not much has turned up. The comet was faint, tucked away in crowded star fields and just plain hard to spot. Maybe there's an old image of it sitting in some archive. Catalina Sky Survey, PAN-STARRS, even those old photographic plates from decades ago. Maybe it's hiding in plain sight, just overlooked. But searching is tough work. You have to guess where to look, which dates make sense. And even then, the comet might be too dim, too close to a bright star, or just too tangled up in the background to pull out anything useful. There's also a real possibility that we just didn't catch it earlier. Atlas only found it in July, and the comet was coming in from a patch of sky that doesn't get as much attention as the ecliptic, where most asteroids live. It approached quickly from the outer solar system, and if it only brightened as it got close to the sun, it might have been invisible until 2025. If that's the case, the lack of early data is just bad luck. We missed it, and now we're working with whatever scraps we've got. Meanwhile, at the Goddard Space Flight Center in Maryland, spectroscopists have been poring over the chemical fingerprints captured by various instruments. The high carbon dioxide to water ratio is unusual but not inexplicable. Interstellar comets formed in different stellar environments. Different stars have different compositions. Different planetary systems have different chemistry, and comets from those systems will reflect those differences. But the spectrum of 3IATLAS has some features that don't match anything in existing databases of cometary spectra. There are faint emission lines in the ultraviolet that could be from exotic carbon compounds, maybe long-chain hydrocarbons, maybe polycyclic aromatic molecules, or they could be noise. Ultraviolet spectroscopy from ground-based observatories is challenging because Earth's atmosphere absorbs most UV light. You need space-based instruments like Hubble's Space Telescope Imaging Spectrograph or the now-retired FAR Ultraviolet Spectroscopic Explorer. And telescope time on those instruments is precious, allocated in tiny increments, always oversubscribed. The features could also be contamination from Earth's atmosphere. Hydroxyl radicals, ozone, other atmospheric constituents can create emission and absorption features that mimic astronomical sources if you're not careful with calibration. Spectroscopy is exquisitely sensitive, which means it picks up everything. Separating signal from noise requires painstaking calibration, comparison with standard stars observed through the same atmospheric column, careful modeling of instrumental response. The teams digging into this data are trying hard not to jump to conclusions. Still, they can't ignore the idea that 3IATLAS might hold materials we've never seen before. If that's true, If this comet's makeup really is unlike anything in our solar system, it could help clear up some of the weird behavior we've noticed. Not all ices act the same. They vaporize at different temperatures. So if 3I-ATLAS is packed with supervolatile stuff, like methane, nitrogen, or carbon monoxide ice, the kind that only sticks around at extremely cold temperatures, it could be releasing gas in ways that just don't fit our usual comet playbook, which mostly comes from watching water ice comets. Take carbon monoxide ice. It starts to vaporize at way lower temperatures than water ice does. When 3I-ATLAS was near the sun, that meant carbon monoxide could be streaming off the comet even while the water ice was still pretty quiet. That might be why we see so much gas being produced, but not a ton of dust. Carbon monoxide molecules are tiny and light. They just don't pull much dust with them as they escape. So the comet can be outgassing like crazy, getting a real push from the jets, but not putting on a big, bright show in the sky. But to really nail down whether this comet is full of weird stuff, astronomers need a whole series of top-notch spectroscopic observations, and they need them across a bunch of different wavelengths. Infrared data helps spot the unique vibrations of different molecules. Ultraviolet shows the electronic transitions and the breakups of molecules. Radio telescopes catch the emission lines for specific compounds. Each window tells a different part of the story, and you need them all to see the whole picture. Trouble is, those observations are getting tougher as the comet fades. By the start of 2026, most ground-based telescopes will be straining to catch enough light from 3I-ATLAS to get anything useful. Hubble or JWST could still manage it. They're incredibly sensitive and can cover a wide range of wavelengths. But there's only so much telescope time to go around, and there are a lot of other things competing for attention. How much time do you spend on a comet that's already heading out of view, probably past its peak for new discoveries, especially when the data so far doesn't give us any slam-dunk answers? That's just part of the deal in astronomy. Sometimes you run out of time. The object slips away. The window closes, and you're left with incomplete data and a bunch of questions you might never answer. All you can do is make the most of what you've got, share your results and your uncertainties, and hope the next visitor from interstellar space is easier to catch. Rotation is another piece of the puzzle. Comets spin as they orbit the sun, and their rotation periods can be anywhere from a few hours to several days. This spinning changes what we see. Parts of the nucleus come into sunlight, jets turn on and off, the brightness changes, and the shape of the coma shifts. By tracking those changes, astronomers can work out how fast the comet spins, which way its axis points, maybe even what the nucleus roughly looks like. With 3I-ATLAS, figuring out the rotation period turned out to be a real headache. Teams tried measuring its brightness over multiple nights, looking for repeating patterns that might reveal the spin. The University of Arizona group used the 1.8-meter Spacewatch telescope, snapping images every 20 minutes for several nights in November. They saw the brightness wobble, but there wasn't a clear rhythm to it. The light curve was messy, could be rotation, could just be random bursts of activity. Another group in Chile, using the TRAPPIST-South telescope, saw the same thing. Brightness changes, but no obvious pattern. They tried all sorts of rotation models, simple sine waves, double-peaked curves for a stretched-out nucleus, even complicated shapes for multiple active jets. None of them really matched the data. Maybe the comet spins very slowly, slower than the observation period. Maybe it's tumbling in a chaotic way. Or maybe the brightness changes are just from unpredictable outgassing, not rotation at all. Without a solid rotation period, the rest of the modeling gets a lot harder. If you don't know how fast the nucleus spins, you can't say where the active regions should be at any given time. You can't pin down the spin axis. You can't build detailed thermal models to show how the surface heats up or cools off as it turns through sunlight and shadow. So, for now, some questions about 3I-ATLAS just have to wait. Attempts to resolve the nucleus directly, to actually image the solid core separate from the surrounding coma, were largely unsuccessful. Even Hubble Space Telescope, with its superior resolution, couldn't cleanly separate the nucleus from the inner coma at 3IATLAS's distance. The best images showed a slightly elongated bright region at the center of the coma, suggesting the nucleus might be non-spherical, but that's as far as anyone could go. No surface features, no definitive shape measurements. Just a bright fuzzy blob. The James Webb Space Telescope, with its infrared capabilities and exquisite sensitivity, could potentially have done better, but JWST time is extraordinarily precious. Every hour of observation has to be justified against competing proposals from astronomers around the world. 3IATLAS, while interesting, wasn't deemed high enough priority for extended JWST observations when there were galaxies at the edge of the observable universe waiting to be studied, exoplanet atmospheres to be characterized, star-forming regions to be mapped. A brief JWST observation in early December captured near-infrared spectra of the coma, confirming the high co-abundance and detecting weak signatures of water and other volatiles. But there wasn't enough time allocated to do deep imaging or extensive spectral mapping. The data was valuable but limited, another example of the compromises inherent in astronomical research. You can't study everything. You have to prioritize. And sometimes interesting objects get less attention than they deserve because other targets are deemed more important. This brings up a broader point about how science actually operates. In documentaries and popular accounts, discoveries often seem straightforward. Telescopes observe, data accumulates, understanding emerges, but the reality is messier. Resources are limited, telescope time is rationed, instruments break, weather doesn't cooperate, funding runs out. Researchers move to different institutions. Graduate students finish their PhDs and leave projects incomplete. Proposals get rejected. The 3IATLAS observation campaign shot high, and honestly it mostly worked out, but not everything went according to plan. Some observations slipped through the cracks, some questions just never got answers. Now the clock's running out. The comet's growing fainter. Our shot at understanding it is fading, and what we have is still an incomplete story. Back in late December, a bunch of researchers scattered across the globe logged into a virtual workshop about 3IATLAS. NASA Goddard ran the show. There were teams from Lowell Observatory, University of Hawaii, Maryland, Arizona, the European Southern Observatory, even some amateur astronomers. The idea was to pool their results, compare notes, spot any oddities, and figure out what observations they could still squeeze in before the comet slipped away for good. Some things were clear. Everyone agreed the comet's path was strange, and the CO2 levels were way higher than usual. The nucleus. Tiny, maybe a few hundred meters, maybe a few kilometers, but nobody nailed down the size. And nobody thought the standard models really fit all the data. But people split on what was actually happening. Some argued the comet was venting gas in weird ways, maybe because it's made of unusual stuff and maybe we missed a big event when it was closest to the sun. Others weren't sold. There were no obvious jets, steady production rates, nothing breaking apart. A few suggested stranger ideas, hidden pockets of gas, a weird internal structure, or maybe something totally unexpected that we just don't get yet. So no big aha moment. All anyone could say for sure was that 3IATLAS is an oddball interstellar comet. The meeting wrapped up with a to-do list for the last bit of observing time, some plans for who'd crunch which sets of data, and a promise to check in again in a few months. Classic science by committee, full of collaboration and compromise, and not always tidy. But there's more to this than charts and data. The people behind these observations aren't just names on a paper. They're scientists who have spent years chasing the mysteries of comets. For a lot of them, interstellar visitors like this are the dream case. A chance to test what we know about our own solar system against something from another star. A shot at learning something truly new about how planets and systems form out there in the galaxy. So yeah, there's frustration. Not at the comet itself. You can't exactly blame a chunk of ice for not cooperating. It's the limits that sting. Limits of what you can do when your target's 100 million kilometers away and your fancy instruments are still ruled by the basics of physics. You bump up against photon counts, fuzzy images, background noise, the shimmer of Earth's atmosphere, and the simple fact that every minute the comet's getting farther away. Picture putting in months of work, fighting for telescope time that most people don't get, juggling schedules with colleagues, hopping the weather holds, tuning your gear, checking and rechecking every detail. Then comes the big moment, the data arrives. And it's muddy. There's something interesting there, but it won't let you pin it down. The error bars overlap. The signal gets buried in static. Your models sort of explain what you see, but never quite lock in what you really want to know. What do? You write the paper. You lay out your findings straight, admit what you don't know, stick to the facts as physics understands them. You suggest possible explanations, but you don't pretend to have it all figured out. More observations would help, you say, even though you can feel the window closing. And you just have to live with that itch of not having a clear answer. That's science most of the time. You work with what you have, not with what you wish you had. You juggle a bunch of possibilities in your head and resist the urge to just settle on one too soon. Look out across the American Southwest. McDonald Observatory in the Davis Mountains, Kitt Peak out in the Arizona desert. Astronomers have spent night after night chasing faint traces of 3IATLAS before it slips away. The images they collect aren't going to reveal the nucleus, and they won't tell us what it's made of, but they'll show us the comet's shape as it heads out, how the coma changes, whether new jets or fans appear, if the thing starts to break up or if it manages to hold together. This watch for fragmentation actually matters a lot. If 3IATLAS does start to fall apart, we'd finally get a look inside. Comets split up all the time after they swing close to the sun. The heat, the gas jets, and the fact that these things are usually just loose piles of dust and ice all work together to tear them apart. If 3IATLAS fragments, you'd see little pieces, daughter nuclei breaking off, each with its own fuzzy halo. The number of fragments, their sizes, how they drift apart, all of that would show us what the original comet was like. Was it a solid chunk or just a heap of stuff barely held together? But so far, nothing. The comet's still in one piece, which is a bit strange. It doesn't prove anything, and it's not a big revelation, just another detail that doesn't quite match what you'd expect. Some people thought, based on how the comet changed direction and lost gas, that it was under serious stress. If it really vented a lot of gas all at once, if it's as fragile as some models say, you'd think it would crack or even shatter. Since it hasn't, a few things could be true. Maybe the nucleus is tougher than anyone guessed. Maybe it's not a jumble of rubble, but something more solid. Maybe the gas release wasn't as violent as we thought, or maybe it just hasn't fallen apart yet. Sometimes comets split up long after they're closest to the sun, once the heat sinks deeper and starts to mess with the inside. So we keep watching. Back in early December, a bunch of amateur astronomers teamed up for an observation campaign. Small and medium telescopes, backyard setups all over the country, California to New York, Florida to Washington, some under city lights, some under real dark skies. For several nights, they all pointed their scopes at 3IATLAS, snapping pictures, hopping to catch any flicker in brightness, any weirdness in the coma, anything that might hint at how the nucleus spins or what shape it's got. They shared their results online, forums, databases, wherever amateurs swap notes. Turns out, the comet looked surprisingly steady. The coma stayed roughly the same shape. Brightness changed just a little, and that could be chalked up to the shifting angles as Earth and the comet moved, or changes in how close the comet was to the sun. No sudden fireworks, no dramatic flare-ups, just a gentle, steady fade, a faint, fuzzy blob drifting across the stars. These amateur observations really matter. Professionals can't watch the same comet every night, too many demands, not enough clear nights to go around. But amateurs can keep their scopes on it night after night, weather permitting, building up a long-term record. No need for proposals or competition for telescope time. Just point and watch. And when dozens of amateurs work together, trading notes and images, they become this sprawling, grassroots network that fills in the gaps professionals can't always cover. But here's the thing. All these observations just make the 3I-ATLAS mystery more ordinary on the surface. The comet looks and acts pretty normal. If you didn't know about the weird path, or you hadn't seen the orbital math showing its acceleration, you'd think this was just another faint comet. Nothing odd, nothing special. Just one more icy wanderer passing through, doing what comets do. It's only when you dig into the numbers, when you compare predicted positions with observed positions, when you try to model the outgassing needed to explain the trajectory change, and then compare that with the observed activity levels, that the discrepancies appear. This is not a visually dramatic anomaly. It's not something you can see with your eyes through a telescope. It's a subtle, technical puzzle hidden in the data, in the residuals, in the small but persistent gaps between expectation and measurement. Honestly, that's what makes this whole thing so unsettling. The universe doesn't hand us its biggest questions with flashing lights or clear signals. They hide in the leftovers, in the weird little gaps between what we expect and what we actually see. Sometimes, you have to just watch and wait. You need patience, careful numbers, and a willingness to sit in the dark with your uncertainty, hopping for more data, not knowing if it'll ever show up. 3I-ATLAS is another reminder that the universe doesn't care about our timelines. It doesn't make things easy. It throws something new at us, and we scramble to make sense of it with whatever tools and time and energy we've got. Sometimes that's enough. Sometimes it is. And sometimes you just have to make peace with the idea that you might never get the full story. You keep going anyway, holding onto your questions, hoping the universe tosses you another clue. Now, as the year turns and 3I-ATLAS drifts farther away, past Earth, toward the asteroid belt, out into the cold, astronomers settle into a kind of watchful waiting. They keep observing when they can. They crunch numbers, update models, write up their findings, send them off to journals, deal with reviews, revise, submit again. Science is slow. It grinds on. But deep down, everyone knows this story probably won't tie itself up neatly. Not now, maybe not ever. We might have to settle for maybes and competing ideas instead of one clear answer. Sure, we know 3I-ATLAS was odd, but we can't really say what made it odd or why. And then, late at night in observatories scattered across the country, when the domes are open and the telescopes are tracking that faint smudge of light, you get these quiet moments. Astronomers step away from their screens, look up with their own eyes, and think about that object slipping away into the dark, taking its secrets with it. And they wonder, what did we miss? What was hiding when our instruments couldn't see? Which questions slipped past us? Did we focus on the wrong things, look away at the wrong time? Will another interstellar visitor show up one day and help everything click into place? Will we look back, years from now, and realize 3I-ATLAS was trying to tell us something we just didn't get? Or will it stay a mystery, just one more odd thing that passed through and left us scratching our heads? The universe's silence isn't empty. It's packed with questions we don't even know how to ask yet. And with its stubborn little mysteries, 3I-ATLAS reminds us that we're still learning how to listen. Part 5, The Open End. Here's what we know. In 2025, something from interstellar space drifted into our solar system. We spotted it, tracked it, and watched it with every high-tech tool we had. At first, it looked like a regular comet, jets of gas, that hazy coma, a path curving around the sun just like you'd expect. But then, right in the middle of all that predictability, it pulled a move we can't quite pin down. It sped up during perihelion just a bit more than our models say it should. The timing. Right when our observations were at their weakest. This isn't some dramatic proof of aliens or mysterious probes. It's just an odd data point, an anomaly. One more place where what we thought would happen doesn't quite line up with what actually did. Science is full of these gaps. Sometimes they wind up being nothing, bad calibration, a missed variable, or just a glitch in the gear. Other times they crack open a door to something new. And sometimes the trail just goes cold before we figure anything out. Right now, in January 2026, 3I-ATLAS is about 400 million kilometers out and getting farther every day. It's too dim for most telescopes. The few that can still see it pick up a fading blur, lost among thousands of other faint sky specks. In a few months, even those glimpses will be gone. Give it a few more years and it'll be billions of kilometers away, a frozen, lonely dot drifting back into the dark between stars. The research isn't over just because it's out of sight. Over the next year or two, scientists will keep publishing papers, analyzing the spectra, plotting the orbit, digging into the light curves. Some will float theories about weird, exotic ices or molecules that only form in alien conditions. Others will argue for ordinary comet stuff, just with strange twists like hidden vents or off-kilter structures. There'll be debate, some back and forth. Calls for better data when the next visitor comes around. But the truth, we probably won't ever know exactly why 3IATLAS acted the way it did. We saw it once for a few months from far away with all the limits that come with that. The data's real and it matters, but whether it's pointing to some rare chemistry, a hidden vent, a gap in our measurements, or something else entirely, nobody can say for sure. Maybe that's where the story should stop. Not with a big reveal, but with a simple fact. We don't always get answers. It's tempting, especially if you're telling this story for an audience, to wrap things up with a neat conclusion. That's what people want: explanations, closure, a sense that it all fits together. But the universe doesn't care about tidy endings. Sometimes the honest thing is just to lay out what we saw, admit what we don't know, and leave it at that. We don't know. Maybe someday we will. Maybe we'll never figure it out. 3IATLAS came from some place we can't see, zipped through our solar system under the gaze of telescopes and sky watchers, did something unexpected, and now it's heading back out, into that enormous empty stretch between the stars. Billions of kilometers, trillions eventually. Distance becomes just a number, bigger than we can really picture. What happens now? That's not up to us. The comet keeps moving along its path, slowing down a bit under the sun's pull, but never enough to stop or turn back. In a few years, it'll reach Neptune's orbit. Give it a few more decades and it'll be out among the frozen leftovers in the Kuiper belt. Wait centuries and it'll pass through the Oort cloud, the very edge of the sun's reach. After a few thousand years, it'll slip away entirely, back into the interstellar dark where it began. By then, whatever happened during perihelion 2025 will be ancient history, a brief moment in the object's multi-billion-year journey through the galaxy. A footnote, if comets kept records. An incident that lasted hours or days out of a voyage that will span eons, that might continue until the stars themselves burn out and the universe grows cold. For us, here on Earth, orbiting our yellow star in a quiet corner of the Milky Way, it's something else. It's a reminder that we live in a universe that is still fundamentally mysterious, that our instruments, powerful as they are, can only tell us so much, that our models, sophisticated as they are always approximations of a reality more complex than we fully grasp, that the cosmos operates on scales and timescales, and according to processes that we're only beginning to understand. It's also a reminder of how astronomy actually works, not through sudden revelations and dramatic discoveries announced with fanfare, not through eureka moments where everything suddenly makes sense, but through patient observation, incremental understanding, the slow accumulation of data points that, over years and decades and centuries, gradually build into a clearer picture of how things work, one measurement at a time, one paper at a time, one question answered leading to 3 new questions asked. Every interstellar object we detect teaches us something. 1/Oumuamua taught us that these visitors come in shapes and behaviors we didn't expect, elongated, tumbling, accelerating in ways that sparked fierce debate about whether outgassing or other processes were responsible. It taught us that our assumptions about what interstellar objects should look like were too narrow, too limited by our experience with solar system bodies. 2I/Borisov showed us something oddly comforting. Some interstellar visitors look just like the comets we already know, water-rich, dusty, behaving exactly as our models predict. It's a reminder that not everything drifting in from the stars is some wild alien thing. Sometimes, the universe runs on the same rules, even across different solar systems. But now 3IATLAS is shaking things up. It's nudging us to pay attention to the weird chemistry that happens in other star systems, to to the wild mix of ices that can form around stars nothing like our own. It's poking holes in our neat theories about how comets release gas, reminding us that there are details, how different ices vaporize, how that changes their paths, that we haven't nailed down. It's making us rethink what's inside these things and how they're built, and it's exposing just how much we can't really see from our telescopes here on Earth. Maybe what we need are more missions that get up close, not just distant observations. And maybe, though we don't want to admit it out loud, it's hinting at something bigger, that objects in space might act in ways our current ideas can't quite explain. That comet is a bigger, weirder category than we thought, built from a handful of familiar examples but hiding a wild diversity out there in the dark. The universe is packed with oddballs, and every time we think we've got it all figured out, something pops up that doesn't fit, just out of reach. Science isn't just about being right. You need the guts to make predictions and see if the universe agrees, but you also need the humility to recognize when it doesn't. Sometimes, you have to live with the fact that the answers aren't clear yet. You can't force nature to follow your playbook. 3IATLAS sits right in that uncomfortable space. It's not so bizarre that we need to throw out everything we know, but it's not exactly normal either. It lives in the gray area, the blurry place where our theories start to wobble, and we have to admit we don't really know what's happening. Funny thing about those gray zones, they're where the best discoveries tend to hide. Not where everything lines up neatly, but in the margins, the odd cases, the stubborn little mysteries that refuse to be explained away. The ones that stick around even after you've double-checked the data, that make you rethink what you thought you knew. History's full of moments like that. Anomalies that everyone ignored until someone finally got curious. Mercury's orbit didn't quite fit Newton's gravity. The difference, just 43 arcseconds per century, seemed tiny, easy to blame on bad measurements or some stray asteroid. But Einstein took it seriously. The result, general relativity, a whole new way to think about gravity. Or take the cosmic microwave background. At first, it just seemed like static on a radio antenna. Turned out it was the afterglow of the Big Bang, one of the biggest discoveries in cosmology. So is 3IATLAS one of those? The kind of oddball that forces us to rewrite the textbooks? Honestly, probably not. The differences are subtle. The evidence is messy. Most likely, it's just a weird mix of ingredients, maybe a strange structure, plus some outbursts we missed because we weren't looking at the right moment. But we don't know that for certain. And the not knowing is important, because it keeps the question open. It keeps astronomers looking, thinking, questioning their assumptions. It keeps the possibility alive that the next interstellar visitor, or the one after that, might provide the context that makes sense of this one. That we might look back in 10 years or 20 years and say, 3IATLAS was the first time we saw this type of object, this class of interstellar comet with these properties, but we didn't have the framework to understand it yet. In the meantime, we're left with observations, measurements, data that points in directions we can't quite follow all the way to their conclusions. And that's okay. That's where we live most of the time in science. Not in certainty, but in the process of working toward it. Not with answers, but with better questions. Not with understanding, but with the tools and methods that might eventually lead to understanding. Think about what it means to observe something from 100 million kilometers away. Light takes about 5.5 minutes to cross that distance. When you look at 3IATLAS through a telescope, you're seeing it as it was 5.5 minutes ago. Not much of a delay in human terms, but it reminds you that observation is always looking backward in time, always delayed by the finite speed of light. And photons are all we have. Particles of light that originated at the sun, traveled to the comet, scattered off its surface or coma, and then traveled to Earth where they entered a telescope and hit a detector. Everything we know about 3IATLAS, its position, velocity, composition, temperature, structure, comes from analyzing those photons. From measuring their intensity, wavelength, polarization, arrival time. We're doing cosmic archaeology with light as our only tool. The limitations are profound. We can't touch the comet. We can't sample its ice directly. We can't measure its mass by weighing it. We can't see beneath the surface. We can't control the viewing angle or the lighting conditions. We take what the universe gives us and try to extract maximum information from minimum data. Sometimes data just doesn't cut it. The signal's too faint, the noise drowns everything out, the timing's off, or the angles just don't line up. Nature throws things at us that we can't figure out by just watching from afar. You need to get up close, really there on the spot, with instruments pressed right up against the thing. Sometimes you have to drill into it, scoop up samples, and run tests in a lab riding along on a spacecraft. We've managed to do that with comets in our solar system. The Rosetta mission from the European Space Agency spent 2 years circling Comet 67P, mapping every nook, sniffing its gases, studying its dust, even landing a probe on its surface. NASA's Stardust mission grabbed samples from Comet Wild 2 and brought them all the way back to labs on Earth. Deep Impact slammed a projectile into Comet Tempel 1 to dig up what was hiding below the surface and studied the debris as it flew out. Those missions changed how we see comets. They proved that comet nuclei are way more complicated than anyone guessed, layered, porous, with different regions behaving differently. They found organic molecules we never expected. They measured stuff that telescopes just can't catch from Earth. But here's the snag. You can't just whip up a spacecraft to chase down an interstellar object the moment it appears. Planning a mission takes years. Building the spacecraft takes years. Even getting there takes years. By the time you've got everything ready, that interstellar visitor is already gone back out into deep space, way beyond our reach. Some folks have suggested we keep spacecraft on standby, parked in Earth orbit, fueled up, ready to launch the moment something interesting pops up. Sounds doable, but it's expensive. You're babysitting hardware in space for years, hopping for the right target, not even sure it'll be worth the cost when it shows up. Take Project Lyra, for example. The team at the Initiative for Interstellar Studies looked into whether we could chase down Oumuamua after it showed up. Bottom line, maybe, but you'd need propulsion tech we just don't have yet. Solar sails, nuclear electric engines, maybe even fusion drives. Regular rockets, forget about it. Interstellar objects fly by too fast and slip away too quickly. With 3IATLAS, the story's the same. Unless we already had a spacecraft out there with enough fuel for a big course correction, it's just not happening. We're stuck watching from a distance, relying on whatever our telescopes can catch, boxed in by time and space. And the real kicker, we have no idea what we're missing. We don't know what a sample return could reveal, or what we'd find by drilling into the surface and checking the ice up close. Maybe a detailed look would clear up all these weird mysteries. So that's how it's built. That's why it acts this way. Or maybe it would throw us a curveball and make the story even stranger, opening up questions no one's even thought to ask. We're not going to find out. 3IATLAS will slip away just like the last interstellar visitor did. Sooner or later, another one will show up and will do the same dance. We watch from afar, scrape together what little data we can, try to piece together the story from fragments, publish our best guesses, with plenty of hedging, and then it's gone before we can really dig in. That's just how astronomy works. We chase things we can't reach. We measure events so far away it's almost impossible to wrap your head around it. All we have are some photons, a lot of math, and whatever insights we can wring from the patterns. Uncertainty is part of the deal because the universe definitely doesn't arrange itself for our benefit. Right now, 3IATLAS is still out there, dim, drifting farther away. It's gliding through empty space, way out where planets thin out and sunlight barely stretches. It's carrying whatever stories it has, whatever happened to it, straight back into the dark, secrets locked away. We're never catching up. We're not sending a probe, not landing on it, not grabbing a sample, not seeing it up close. We'll never really know it, not the way we want, but we saw it. We measured what we could. We argued about the mysteries it tossed at us. We took notes, logged its passage, and added it to our growing list of things that don't belong here. Reminders that our solar system isn't an island. Stuff drifts in from the galaxy. Stars swap debris. Comets and rocks just wander, slipping through the space between suns. Even the unanswered questions have value. They remind us how much we don't know, how enormous all this is, how objects can surprise us in ways we never expect. There's a ton left to figure out. Somewhere way past Mars, near the asteroid belt, 3IATLAS is gliding through the dark. No sound, no show, no drama, just the slow, invisible loss of whatever ice it had left. Just movement, just physics. The sun's gravity tugs, trying to slow it down, but it never really stops, never catches it, never makes it ours. And here on Earth, astronomers everywhere keep thinking about it. Still crunching numbers, still writing, still tweaking theories, still wondering. What did we miss? What should we have looked for that we didn't? What will we do differently when the next one comes? There's always going to be a next one. Interstellar objects aren't as rare as we used to think. We're getting better at spotting them. New instruments, wider sky surveys, detectors that pick up the faintest signals, and faster computers to handle the avalanche of data. Soon, the Vera C. Rubin Observatory will scan the whole visible sky every few nights, catching moving objects too dim for us to see with current tools. The Nancy Grace Roman Space Telescope will work from space, using infrared eyes and leaving Earth's atmosphere behind. Add in fresh radio telescopes, sharper spectroscopes, and machine learning algorithms digging for weirdness in mountains of numbers. The galaxy, it's messy. There's debris everywhere, material tossed out of planetary systems as new worlds form and giant planets throw their weight around. Comets get kicked out by close brushes with monsters like Jupiter or Saturn, or their alien cousins around other stars. Asteroids get flung out by complicated gravitational dances. The Milky Way, no matter how empty it looks, is packed with this stuff. Billions and billions of objects drift between the stars, most of them dark and frozen, invisible unless they wander close to a sun and briefly shine. We're not sitting still either. Our solar system barrels through this interstellar junkyard at about 230 kilometers per second, circling the center of the galaxy with countless other stars. We're moving. We meet whatever crosses our path. Some of it just passes by. Some we manage to catch. Some we get to study up close. Every encounter teaches us something new. Oumuamua showed us that interstellar objects can look and act in ways we didn't expect. Borisov reminded us that some are pretty normal. Then there's 3IATLAS, which makes it clear we're still missing pieces, that our ideas are incomplete, and that nature loves to surprise us. The mix of interstellar objects is wild. Some are icy comets, some are rocky like asteroids, some blur the line between both. Some formed close to their stars, others far away. Some got tossed out while they were still young, others spent billions of years circling before getting kicked into the void. Each one carries clues, a snapshot from a different system, a different star, a different story. With better tools, we'll find more of these cosmic visitors. The Vera C. Rubin Observatory alone might spot dozens, maybe hundreds over its lifetime. With that, we'll finally get a real sample to work with. We'll start to see patterns in their orbits, their makeup, their quirks. We'll figure out what's normal and what's rare. Our models for how planetary systems shed their debris and how that debris travels across the galaxy will get sharper. Every new discovery is a chance to test our theories, improve them, ask better questions. A chance to see what the universe throws at us next, what puzzle, what challenge, what surprise. And every time we learn, we tweak our models, we broaden our definitions, we inch closer to understanding just how wild and diverse the universe really is. Every object adds to our catalog, fills out our database, and deepens our grasp of how planetary systems grow, change, and interact with the galaxy around them. We're going to run into more weird stuff, more objects that don't fit the patterns, more data that just piles up questions instead of answers, more moments where our predictions and the reality in front of us don't match and there's no quick fix. But that's not a sign we're failing. That's what science looks like when it's actually doing its job. The universe doesn't owe us anything. It's not here to be understood. It doesn't care if our theories work out or if we're making sense of its patterns. It just exists, huge, old, tangled up in complexities we can barely wrap our heads around. It runs on physical laws, and we're chipping away at those bit by bit, observation by observation, experiment by experiment, theory by theory. And it's us humans trying to figure it all out. We don't have perfect tools. Our view is always limited, and we're not here for long. Still, we keep going. We build telescopes. We code. We teach new scientists. We ask questions, take measurements, publish what we find, and argue over what it all means. Piece by piece, we're building some kind of picture, however incomplete, of how the universe works. 3IATLAS is already fading from the headlines if it was ever there at all. Most people will never hear the name. Even those who do will forget about it soon enough. Other things will fill the space: politics, money, celebrities, sports, the stuff of everyday life. People carry on with what matters to them. Meanwhile, the cosmos keeps moving, not caring if anyone's paying attention or not. But for the scientists who spent months chasing this thing, gathering its light, puzzling over its strange behavior, it sticks around. It's the comet that refused to play by the rules. The data set with those stubborn, unexplained blips. The object that asked questions nobody could quite answer before it vanished. They'll remember it. Next time they point a telescope at a new visitor, write a new grant, or sketch out a new model, 3IATLAS will be in the back of their minds. And at some late hour, deep in another project, staring at another unexplained signal, their thoughts will drift back to that weird acceleration at perihelion, to a gap in the data, to the odd feeling of not really knowing what they were looking at, that nagging sense they missed something, that the answer was just out of reach. If only the weather had been better, or the instruments sharper, or the timing right, they might have cracked it. They'll wonder, did I overlook something? Was there an observation I should have pushed for, a question I didn't ask in time? That feeling doesn't really fade. Not exactly regret, more like fuel. Next time they'll dig deeper, question their assumptions harder. Remember, the universe is always a step ahead, always more complicated than it looks, always ready to remind us how much we don't know. That's what 3IATLAS leaves behind. Not its name, not its orbit, not the details in some table. What matters is the reminder: discovery is messy. There's always a limit to what we know. Real understanding takes patience and stubbornness, because the universe won't just hand over its secrets. It moves on its own schedule, not ours, and it doesn't pause for us to catch up. It came out of the dark, crossed through our little patch of light, through that thin zone where we can actually watch and measure and wonder. Then it slipped away again, back into the shadows, leaving us with a pile of questions and that old, familiar feeling that there's always something more we're missing. And maybe that's exactly what we needed. It's easy to forget how much we don't know. The universe keeps throwing curveballs, reminding us that our theories are just sketches, not finished portraits. Every so often something comes along, something we didn't predict, and suddenly we're back at square one, realizing our sense of certainty is just a comfort blanket we cling to when we get too sure of ourselves. Take 3IATLAS. It's slipping away now, already too dim for backyard telescopes. Soon, not even the pros will be able to spot it. After that, it's gone from sight, just numbers and notes in databases, tucked away at NASA, universities, observatories. The data will sit there, waiting. Maybe someone will dig it up in a few years with a new idea or a better tool, and suddenly, what didn't make sense before will click into place. Until then, all we can do is wait. Watch the skis for the next oddball. Get ready for whatever shows up next. We have to let the big questions hang in the air, without demanding neat answers, without expecting the universe to play by our schedule or soothe our curiosity. That's really what it means to study space. You learn to live with not knowing. You make peace with mystery. You remind yourself to stay humble, because we're surrounded by a cosmos bigger and stranger and more beautiful than we can possibly grasp. Stuff happens out there we haven't even dreamed up yet, and some of the rules are still a mystery. 3IATLAS pulled off something NASA can't explain. The timing, weird enough to make even seasoned scientists stop and wonder. But maybe chasing an answer isn't the whole point. Maybe what matters more is sitting with the questions, being okay with not knowing, having the patience to wait for better tools and better data, and being brave enough to admit we're still learning. What else is out there that we haven't learned to see yet? Who else is out there heading our way? They're carrying questions we haven't even thought of, ready to shake up everything we think we know. One day we'll have the right tools. We'll ask questions that right now wouldn't even cross our minds. When our instruments get sharper, our models get smarter, and we finally look at the universe with clearer eyes, we'll start to see patterns in the chaos, answers to puzzles that leave us scratching our heads today. The universe doesn't care. It just keeps doing its thing, running on laws we're still trying to write down, moving along with or without us. It doesn't rush. It doesn't wait for us to catch up. Whether we understand it or not, it goes on, totally unbothered by our need for tidy explanations. But we keep watching. We measure, we wonder, we tinker with better telescopes, send more curious minds into the field, pore over mountains of data, put our thoughts on paper. It's slow work, messy sometimes. But that's how we do it. One observation at a time, one oddball result at a time, one stubborn, unanswered question at a time. 3IATLAS fits into this big, messy story. Maybe it's just a footnote, or maybe it's something more. Nobody's writing a neat ending for it anytime soon. But it's in there, tangled up in our long, restless effort to figure out what's really going on out there, to find a place for ourselves among all these stars and galaxies, and the weird, shadowy stuff that fills up the gaps. And somewhere far off between the stars, out in that deep, cold stretch where suns blur into pinpricks and time just drifts by unnoticed, 3IATLAS keeps on moving, silent and stubborn, following its path through the dark. Silent, alone, carrying whatever it is we couldn't quite figure out, whatever secrets remain locked in its ice and rock and organic molecules. Moving through the cosmic night at its steady velocity, neither accelerating nor decelerating noticeably now that it's far from the sun's heat. Going somewhere we'll never know, following a trajectory we can calculate but never truly understand, headed toward some distant point in the galaxy, or perhaps toward intergalactic space, to wander the void between galaxies for eons. Leaving us here, on our small blue world orbiting our ordinary yellow star, looking up at the sky with our telescopes and our instruments and our insatiable curiosity. Wondering, always wondering, what was it? What did it mean? What did we miss? And the universe, in its infinite patience and indifference, offers no answer, just the slow wheeling of stars, the patient motion of planets, the endless arrival and departure of visitors from the dark, and the knowledge that someday, perhaps, we'll understand. But not today. Not yet. Maybe not ever. And we have to be okay with that.